Hi everyone, Mr. Eric Kwa here, founder of Mr. Khemistry. Hope you're enjoying the videos that I've made for you specially. Remember to tap that like button and to click subscribe and to share with your friends if you found any of these videos useful or interesting. I look forward to seeing you around. Let's get started with today's topic.
Hi everybody. So today we'll be going through NYJC Prelim 2017 Paper 2 Question 2. This question is on kinetics and let's dive right into it. So we are starting with 2-iodobutane here, which I will short form call it RX, halogenyl alkane, can be converted into 2-aminobutane. Okay, so you know that it's becoming amine. RX convert to amine, it is most likely a nucleophilic substitution reaction. Okay, so they have given us the equation right here. See that the iodine was substituted by NH2, right? NH2 substituted in, the iodine substituted out. So in order to determine this rate equation, you have a kinetic investigation. Okay, so they've given us some of the data. 4 moles per dm cube of this ammonia was first prepared. Okay, so this one is just for our information. Okay, then subsequently they said equal volumes of 0.2 mole per dm cube of the RX and 4 mole per dm cube of ethanolic ammonia were mixed. So whenever you see equal volume, right, you got to be careful. Equal volume, right, when you mix the equal volumes, the concentration will halve. So this concentration becomes 0.1 mole per dm cube, and this concentration becomes 2 mole per dm cube. Right, so then they say at suitable time interval 10 cm cube, 10 cm cube was pipetted out into a conical flask and quenched. Okay, so you mix them together in a conical flask, right? They will mix. You have the RX plus the ammonia, right? So they will mix together and 10 cm cube was pipetted out. Okay, so 10 cm cube. Okay, at various time intervals. So it was pipetted out, 10 cm cube, and so on and so forth. Okay, so then they say chlorine gas was bubbled into the reaction mixture and excess gas was removed. Why was chlorine gas bubbled into the reaction mixture? You must remember, right? After the reaction, there will be some I minus. Okay, there will be some I minus that was produced. So when you bubble in chlorine, right, chlorine will displace the I minus, so you'll get chloride, and then you'll get back the iodine. Okay, so I minus will be displaced to get back I2. It is a displacement reaction, right? Chlorine gas, you're doing a displacement. Okay, just take note of that. Okay, then the reaction mixture was titrated with 0.025 mole per dm cube of thiosulfate, okay, in the presence of an indicator. Okay, so titrating, what are you titrating with the thiosulfate? Obviously, you're titrating the I2, right? This I2, you're going to titrate with thiosulfate. Okay, so the I2, converts back to the I minus. Okay, all right, let's now look at the question itself. Draw a labeled diagram, right, to illustrate the bonding between ammonia and ethanol. Okay, so this bonding has to be hydrogen bond. Both ammonia and ethanol actually have hydrogen bond in their molecules, but they also have hydrogen bond between these molecules. Okay, so I just want to zoom in here for you to take a closer look. There's two ways of drawing this hydrogen bond. Not two ways, basically two atoms that can form this hydrogen bond. It can be the H from ethanol or it can be the H from ammonia. Both works. Okay, what is important here, right? You got to remember the dipole moment, right, has to be between the H and the O or the H and the N that are covalently bonded. Okay, all right. Do take note that this delta minus, right, is not that critical. Okay, so we are only marking for this dipole moment, this dipole moment. Okay, and then the next thing is we want to see the lone pair right here that accepts the delta positive H. Okay, and then subsequently we want to see the hydrogen bond labeled properly. Okay, so 3 points, you got to have the dipole moment. One, you got to have the dipole moment written properly. The second point is you got to have the lone pair. And the third point is you got to label the hydrogen bond. Okay, so if you have these 3 points, yeah, the marks will be awarded to you. Okay, so that's for A. Let's look at B. Suggest why the reaction must be quenched. I think this is a fairly common question, and sometimes they will ask you, how can you quench the reaction? Okay, generally speaking, right, most reaction you can quench them by adding a large amount of cold water that will reduce the kinetics drastically. Okay, or you can basically add in something that neutralizes or reacts away the catalyst. Okay, so in this case, we can add in large amount of cold water, and we can also add in large volume of acid to remove the one of the reactants. Okay, so the second way that you're doing this, right, is basically contextualize for this question itself. Okay, now, second one, write a ionic equation for the reaction chlorine. Okay, so this was the displacement reaction. You just basically got to make sure that it's balanced. Ionic, it has to be ionic. Okay, so don't write in the rest of the NH4 plus. Okay, then ionic equation between the I2 that was produced and the thiosulfate. Okay, so this is a pretty famous equation. I2 iodine being reduced by thiosulfate back to I minus. Okay, suggest a suitable indicator. This again is a very common question, starch indicator. So one point to take note, right? When you say you add starch indicator when it turns pale yellow, right? Why do we add it only when it turns pale yellow? At pale yellow, right, you have very low iodine concentration, so that you know the complex, right? The complex that iodine forms with the starch, right, is not too tightly bind together, all right? So that the complex uh, is not too tightly bonded, okay? Because if it's too tightly bonded, right, then it's very difficult for starch to release the iodine to be titrated by the thiosulfate. Okay, so we need to wait until it's low concentration, which is pale yellow. Okay, then we add in 1 drop of starch, right? So that the color change, right? It goes from pale yellow by right to become colorless, right? This is very difficult to see color transition, but if we convert this to blue black, okay, the blue black complex, then this transition, blue-black to colorless, is very stuck, is very obvious. Okay, this transition is very obvious. Okay, so that's the reason why we want to add the starch indicator near to the end, because this color change is a lot more abrupt, very obvious. Okay, now let's look at the next part, part C. Table shows the result obtained from the titration. So you have time, and then you have the volume of thiosulfate used. Okay, to determine the order of reaction with respect to 2-iodobutane, use the data to plot a suitable graph. So thiosulfate, right, is titrating the iodine. The iodine is like the product of the nucleophilic substitution, because iodine came from displacement. Okay, so basically NYJC, they have one additional step. So when you have the Rx, right, reacting with ammonia, you get amine, and then you also get the I minus, right? I minus. This I minus, right, is then displaced to become I2 by chlorine. Then this I2, right, is then titrated by thiosulfate. Okay, back to I minus for O6. Right, so there's like one more step, right? Usually for questions, right, that they do the nucleophilic sub, they straight away titrate the product so that you can link it very quickly. But NYJC, they have another two more steps. They displace the iodine out, and then they titrate the displaced iodine by thiosulfate. All right, so we are monitoring the thiosulfate here, but the thiosulfate, right, is linked to your iodine by a certain mole ratio, 2:1. And then this iodine, right, is linked obviously to the I minus, which is linked to the I minus initially. And this I minus obviously came from your Rx. Okay, so if you want to find the order of reaction, right, with respect to 2-iodobutane, the Rx initially, right, you can actually do it via the product curve. Okay, the product curve for thiosulfate. So you can see the highlighted species, you link it all the way back to Rx, taking note of all the mole ratio. All right, so the challenging part here is to link back the thiosulfate all the way back to Rx. Okay, okay, so we can see that this is a product curve. Obviously, right, you will need to work out, what is the end amount, the final volume of thiosulfate that is needed. Okay, so if you work out the thiosulfate amount, right? So basically we link it the way that I was telling you guys about. You link thiosulfate back to your 2-iodobutane, your Rx. So it's 1:1 all the way basically. So you work out the number of moles, right? So this is basically the concentration of your thiosulfate, if I'm not wrong, 10 cm cube. Okay, so this is the number of moles of your Rx, okay, that was titrated by your thiosulfate. Okay, so you link it all the way back, right? You divide this by the concentration which was given by the question. Okay, then you find out that the total amount, the final amount of thiosulfate required. Okay, this is the final amount or total. Okay, we need to find this final or total for all product curve, because all product curve, right, you need to find the at the end how much was needed. All right, so that we can construct the half-life. Okay, so final amount was 40, right? So at the halfway mark, 50%, and then at the 75% mark is at 30. Okay, so you construct first and second T half is more than enough. You get around 9.5 minutes. So therefore, constant half-life tells you that it is first order with respect to the Rx. Alright guys, so I hope this is pretty clear to you. If not, you can always rewind back to the start of the explanation and then hear it again. Alright, let's move on to part 3. If the concentration of the ammonia, right, is halved, new series of experiment carried out, they say the gradient at each point was halved as well. So if concentration is half of your ammonia, which is your nucleophile, then the gradient, which means that the rate is halved as well. Concentration half, rate is half, means that it is first order. Okay, means that it is first order. Okay, so this is pretty straightforward. So since we know that both are first order, we can construct this equation, rate equation. Yep. Okay, part 5, calculate the rate constant for the reaction between 2-iodobutane and 4 mole per dm cube of ethanolic ammonia. Okay, so this one you basically just need to use the formula and substitute in your values. Okay, so what is the formula, right? Because it is a pseudo first order, the formula is T half equals to ln 2 over K times the reactant that is in excess. Okay, the one that is in excess. And we need to remember, right, the one that is in excess, you have to use the concentration after mixing, because remember earlier on we say that mixing is equal volumes, right? When you mix equal volumes, concentration is halved. So from 4 mole per dm cube, it goes to 2 moles per dm cube. So we substitute that in with the half-life that we got earlier on, we are able to calculate A. Okay, do not forget about the units here. Okay, for part 6, right, hence describe the mechanism. So this part is evidently it is SN2, okay, because both are first order, right? So both the reactants and the nucleophiles are first order. They will affect the rate of reaction. Okay, so this mechanism, I will leave it to you to look through. Basically, it is the standard mechanism, one of the 6 that you have to remember for your A levels. All right. Okay, suggest and explain the effect of the rate of reaction when 2-iodobutane is replaced with 2-chlorobutane. So the difference between these two, right, when we are trying to do nucleophilic sub, we have to remember, in order to do nucleophilic sub, you have to break the CCl bond, okay, the CX bond. Okay, so what is the effect on the rate of reaction? You look at the bond energy, right? So more bond energy required to overcome the CCl bond. So the rate of reaction actually decreases because it's harder to break this new bond. For second part, they say if the nucleophile now is replaced with ethanolic ethyl amine. Okay, so what is the difference? The difference is this guy is just NH3, right? This guy has NH2 and then it has a R group of ethyl. Is okay, so CC, right? This ethyl group is electron donating, which will make the lone pair more available and make this a stronger nucleophile. All right, so we got to phrase it properly. Increases the electron density, making the lone pair more available, okay, or make it more nucleophilic. So the rate of reaction actually increases. Okay, so they want to show you, right, the 2 factors why they are each first order. Okay, so because let's take a look at this. You have your Rx. Okay, you need to break this bond, right? And then also the rate depends on the nucleophile that is attacking your carbon. Okay, so this is your nucleophile. which is first order, and then this is your Rx, right, which is your electrophile, is also first order. Okay, so this depend on the bond energy to break, and this depends on the nucleophilic strength, okay, availability of lone pair. All right, so that is the whole question from NYJC. Hope this helps.